this one says 95, right? So what is this another way of saying what this is asking for? I want to do a little bit of solving first, right? What's the first step here? Yeah. Good. So subtract the 1. And now we know.
We can just put it into this.
Beautiful, because then this is a question about finding the what?
Third power.
Third roots. I love it. Cool. Yeah, I see. I forgot what I was going to say. Oh, so, for example, if I said what's the 14th root of 1, here's a little interesting side note. So to get into this, we figured out what the square root of I was. I thought that might be a pull for some of you that are like, yeah, what the hell is that? Well, you tell me what I is, and even if you didn't, now you know. Even if you didn't want to know.
You're like, hell no.
But now if I said, what's the 14th root of 1? I don't know if you guys understand that how many roots are there?
14.
You've given me one of them. Do you understand? I don't know. I don't know if you understand. Because here's 1. One of them is 1, and then there should be 13 other ones equally spaced around here. That's the geometric interpretation behind what this process does of finding roots. So there's all these other possible roots for every single number alive. So we thought that the 14th root of 1 is 1. This is true. But then there are other 13 other possible answers. Right? So, and actually, to be more precise, to be plus or minus, so it would be x to the 14th power equals 1. There are 14 answers to that. Freaky. There are nothing you could possibly really get easily by doing this. Now, if I gave you this problem, what would you do? If I said you couldn't use radicals, what would you do? What would you start to do? Yeah, break it and factor it. So you can do one step easy enough. And then pretty much after that, you're screwed, right? You don't have I know how to do something to the third power, and big dude, little dude, but 7th power, really big dude, then really tiny dude, then really big in the middle dude. No, I don't know what the hell that is, right? I don't know what that is. But this process gives me a way to figure it out relatively easily. Just because we've rewritten the complex number in a more visual format, using the idea of polar coordinates.
You say relatively. How?
Well, because what is the process? I mean, what's z to the 1 over n?
Z to the 1 over n. Oh, r to the 1 over n.
I love it. R to the 1 over n.
Cosine.
And over.
K divided by n. Plus 2.
Plus 2 by k.
Plus.
So they're the same thing here, right?
And plus 2 by k over n.
Cool. And it makes sense because when I raise a complex number to a power, I multiply the angle, right, by n. So when I take a root, I should divide. It makes sense. When I multiply two complex numbers, I add the angles, I multiply the r's. When I divide two complex numbers, I subtract the angles, divide the r's. Beautiful symmetry, easy to memorize, like you guys have to. Okay, so what this is really asking for then is, what is this?
Yeah.
Cool. So the first thing I got to do is put this piece into the right format, and then I just have to apply that idea to it. Right? Bless you. So you guys think about it, this will go into that format really easy.
Yeah.
So go ahead and do that. Put it into polar form. Just be careful, what quadrant are we in?
Third.
Good, because you're both negative, I like it.
5 pi over 4. Oh.
Put this word general is always forget.
Do you actually want us to like solve it too?
Well, no, I'm going to catch up to you now. Just let people settle out. So this part here in this format is what?
Right.
What?
Yeah.
Yeah, putting this number into this format, you get
Oh, right, 2.
right to
Cosine 5 pi over 4 plus I sine 5 pi.
kick ass. Stop right there for a second. You get a lot of stuff like this where it's actually relatively easy, or at least old math, right? Relatively old math. We should know how to get the angles for certain things now. But it's just so different that we're not used to it. But it actually is relatively easy. Even this weirdness should be relatively easy to understand if you think about it. We've encountered this kind of thing before, so there it is again. It all makes sense.
Yep.
And the beautiful thing is, once you get it in the right format, it's just a plug and chug situation. And it isn't difficult to remember this idea, this formula. Shouldn't be. So we put this in there. So I call this W real quick, just make sure that everyone understands it's not the same as that Z. I'm not taking the third root of the Z, I'm taking the third root of this. So that's like my W there. Is that cool? Just write Z on that side. So what is that to the 1/3 power then?
It'd be red.
Rad 2 to the 1/3.
Or you could do
5 pi equals 2.
Same thing. Okay, so that's
Wait,
not very
isn't
exciting.
it 3 and not n?
3, yeah, I think. And now you just got to figure out what all the answers are. How many answers will there be? 3, and each of those will have k equal to what? K equal to
1,
0,
0,
1, 2. I like it. Yes, sir.
Just going back, when you did theta, b over a was 1 over 1, or negative 1 over 1?
Negative 1 over negative 1.
That's mostly just for your
So isn't that 1 over 1 still?
Sure, it could be. You just got to be careful about which quadrant you're supposed to be in.
Okay, so that you have to reflect on the.
Because there you would be negative 1, you'd be there. You'd be in the
Okay,
third quadrant.
okay, now I know.
So this is more than just, how do I say this? That has got to point to the same point that this does. Therefore, they must agree with what quadrant they're in. So whatever you get from the inverse tangent, you just got to look at it as a reference angle, unless you're lucky and it's in the same place as, if it's in the first or fourth quadrant, you're good. If it isn't, you just got to be careful. So let me see if we can get some more room here. So if I let k equals 0,
what we're actually like going to do it.
what do I get here? I get 2 to the 1/6 times, of course in there I'm going to get 5 pi over 12. I'm going to get whatever the hell that is. We have a way to do that. It's half of 5 pi over 6, but screw it. What do you get in the calculator? If you do cosine of 5 pi over 12, and it's not too bad. You just plug that number in there. Just approximate that.
0.2588.
So roughly 0.259. Just
Right.
throw that in there.
Yeah.
Multiply it through. Make that a decimal if you want to. I mean, you could be more or less careful about rounding errors. I mean, here again, we could get an exact expression for this using the half angle formula, if you really, really needed to. We don't really need to for right now. K equals 1 would look like what? Cosine of
5 pi over 12.
Let's make this a little bit better here. This will be 5 pi over 12 plus 2 pi k over 3, which is 5 pi over 12 plus 8 pi k over 12. So at 0, 5 is 5 pi over 12. At 1, it's 13 pi over 12. And and then at 2 it's what would it be? Just add another. So we've done this before, where if you're adding stuff, you just make it LCD right there.
Yeah.
If you add none of them, you get 5 pi over 12. That's k equals 0. If you add one of them, you get 13 pi over 12. If I add 2 of them, you get 16 plus 5, 21 pi over 12, which you can reduce, but it doesn't really matter as long as you don't flip the numbers around. There you go, Jeff. You get your 3 answers. So it's kind of nice. You know exactly how many answers you get. If I try one more time, I'm going to rotate again on top of an answer I already got. Right? There you go. So it's nice. Let it be nice. It's not that evil, really. It's just new.
For each one, is 2 going to remain to the 1/6 power?
Yeah, R is the same for each one of them, right? It's 2 to the 1/6. So yeah, that's not dependent on K or N or anything. Yeah. And the only thing with N was the 1/3 power. Okay, good. So you should be able to transform any complex number into this form. Once you have it in this form, you could raise it to whatever power. You could take any root of it you want to with those processes there, right? That formula. All right, cool. And again, just take some practice. So you haven't done the homework yet. You haven't got the practice yet. Okay, so anything else from homework? That was a really good review of like almost everything. Exactly. Anything else from homework? 8384. Okay. Let's get back into 84. Let me look at that handout I gave you guys last time again, because a few of you guys weren't here. Anybody else come in and not get that from the other day? Sure.
They win their were state champs. That's it.
So you do me a real quick favor and shut out one of those lights. Can you do that? The one that says hi. Yeah. Cool. All right, so very quick. I mean, whoever was here, we did this last time. Just to remind us, we have this thing, and we had an example the other day about like temperature behind the scenes. Temperature would increase sales of water and ice cream. Right? So we can have tea behind the scenes. So you can say, why would selling a lot of ice cream suddenly increase the amount of H2O within themselves? Right? And then we realize, it's really temperatures behind the scenes. So here, tea very often is considered time, but it's good to realize from the beginning that it doesn't have to be time. It could be almost anything. In statistics, you get this kind of thing when you talk about correlation between two variables, and there could be something behind the scenes that's correlating both of them, just like the ice cream and the water example. However you say that word. So -1, 0, 1, 2, 3. So that kind of makes sense. It's a good place to start. Depending on how quickly this thing moves, depending on the functions they're described by. So these are pretty easy. These are a straight line and a cubic, so that's not going to be too freaky. But if I am there like sine of 40t, that bad boy is going insane. I probably have to plug in a lot more points in the middle. I probably want to plug in like every 10th of a point. That would be an awesome problem for me to give you.
Well, this is graphing hell.
Exactly. Thank you. So I should be used to it. Dante was here. What would X? So we did this the other day. So very quickly, just remind me when you plug a -1 here.
-4.
And for Y.
5, 0, -3, -2, -1, -4, 1, 0, and 3.
Okay, cool. So that's what we did last time. It's just plug and shove. Let it be plug and shove. You got a little bit beefed up XY table, and you now got a T back there controlling both of them, right? But you end up just graphing these. Be very careful. This doesn't actually show up explicitly. So then you graph those, -4, -5, 0, -3. How we doing? -2, -1, -4, 1, and 0, 3, like that. So it does that S thing we saw last time. Cool. So they have to give you what X and Y are defined to be in terms of T, and they have to tell you what T does. They have to give you some kind of range for T. Now, if they're sine and cosine, maybe they don't have to because it kind of retraces itself. But this thing, of course, would go forever off in both directions. If I just turn this, it becomes a normal cubic. Did we? Yeah, we did part B last time too, didn't we?
No.
Okay. So, I'm sure we did. So if we take, which one of these is easier to solve for T? Yeah, and this is not the way you always do this, but this is the first way I try. If I'm trying to eliminate a variable, I've got basically 3 variables up there, right? If I try to kill the T, the first thing I think of is substitution. Sometimes there might be a much more direct way. If X was T and Y was 2T, then Y is twice X. I mean, I don't have to really think about that. But here, if I solve for T in the Y equation, I get Y plus 3 over 2. Is that cool? Add 3, divide by 2. And then just plug that bad boy into the X equation. So X would be Y plus 3 over 2 cubed minus 3 times Y plus 3 over 2 squared. Let me stop right there for a second. So we see where that came from? Because it was T cubed minus 3T squared. So I just replaced the T's with what they are. And I mean, if I wanted to, I don't really feel like foiling this bad boy out, and you don't have to either. It'd be 1/8 Y plus 3 cubed minus 3/4 Y plus 3 squared, and then you could even factor it if you wanted to. It all depends on where you want to go from there. All right? Stop there for a second.
Okay, now solve for Y.
Yeah, you want to solve for Y? Why do you think it's difficult to solve for Y?
Because
You can tell from the graph, because the graph is that a graph of a function. Is Y a function of X? No, why not? It does not pass the
vertical line.
and then vertical lines. That's good. I like it. Cool. Yes, ma'am.
How'd you do that?
Magic.
I don't.
It's a world of illusion. Huh?
I don't think magic applies to this field.
All right. You are just too correct. Which step did I lose you on? You're okay here?
Yeah, that part's fine. I'm just.
And then plug it in?
I'm okay with the plugging in
Cool.
too. It's just that I don't understand how you got 1/8 out of.
You cube the 2 and you get
And 8.
8 on the bottom. Yeah.
Okay.
So you can't just take the 2 out. There's actually 8 because you have to cube it first. It's just like you can't take, if I had square root of, this is the kind of thing that kills my calc students. If you had square root of 4x minus 4, what could you do with that?
Nothing.
Factor
You
it?
factor 2 out.
Yeah, don't make it 2x minus 2.
Well,
Dude.
factor
That's
4
magic. So I agree. Magic has no point, no place.
Maybe 4 times x.
Yeah, take a 4, but you can't take a 4 out.
4
The
x
square root
minus
of
1.
4.
Take square root of 4 out. Yeah. So it'll be 2 square root of x by 11, right? So that's the same thing I'm doing here. I can't put it out here unless that happens to it. I can't put the 2 out here unless that happens to it. That's why there's a 4 down there. 2 squared is 4, so all right, cool. So please, that should be the stuff we're just eating up. I mean, that should not be a problem. We should be able to do calculations like that, no problem. Yes, ma'am.
So there's like nowhere else to go after we get to that solution. Okay.
Oh yeah, there's places to go. Depends on what you want to do. You can cube this and square that, get your like terms together. I don't feel like that. You could take 2 y plus 3's out, add a 1/8 out. Why not? All right. What would that look like? Let's see. So I got 1/8. I saw some of you guys visibly go, "Oh, come on."
Pull it down.
I just want to write it first. So let's see if you guys can handle this.
No.
So if I take a 1/8, how many y plus 3 is going to take out?
2.
2. The one that's going to freak you out is the 1/8. So I'll do the first one. What happens over here?
It's 6.
6.
Kick ass. Look at that. That's my 5th puberty. So if I take a 1/8 out of here, doesn't this get 8 times bigger? If I take a 1/8 out of something, it gets 8 times bigger. So this is just going to get 8 times bigger. 6. Don't let that be a big problem. And how many of these are left?
0.
None. So I get 1/8 y plus 3 squared times y minus 3. That looks pretty useful.
I was really confused because you left out the square, but you left out the what? Wait,
What happened?
no. No. I'm
Yeah, there's only one of these left here, right?
Yeah, I was just wondering where. Okay, sorry.
It's all good.
Yeah, I was overthinking.
That is easy to do. Yes, ma'am.
You just said it needs to be 8 times bigger and then you didn't do that.
Sure, I did.
Yeah.
Yeah, what was here before? 3/4. What's 8 times bigger than that?
No, but what about the first part?
Yeah, what's 8 times 1/8? 1. Yeah, okay. Because I took the 1/8 in that one, you almost don't even think about that because you're taking a 1/8 out. But to help you, if there's something in there already, when you take something out, you divide it out. So you multiply by the reciprocal. And that kills some of my students. And that should not be an issue. Should not be an issue. Alright, so let's do this. Let's see how it works in the graphing calculator.
Which one? Yeah, the bottom one? Or?
Yeah, let's do the top one first. Let's just recapture that. And then we'll do the bottom one also. It wasn't as this one or that one.
So what is Cartesian's equation then?
Rectangular coordinates.
Oh, okay.
Yeah, Cartesian is your Descartes, the
X,
XY plane.
XY.
There.
So if you ever see the words Cartesian, that is one word. So I'll say the word Cartesian, that refers to XY plane.
What are we doing now?
Wait for the computer to come up.
Oh.
So let's do this real quick. You'll love this.
Oh, yeah.
You know that, trust me. We're going to graph this as soon as this thing comes up. Can you guys see how to eliminate the t? Do you want to solve for t?
No.
By God, no. Please, dear God, do not do that weirdness. But look here. If y is 5 cosine 2t, then cosine 2t is y over 5. That's amazing. And so right here I could put
Cosine 2t.
times 3. Yeah, exactly. Kick ass. So the only part that's a little weird, of course, is this guy.
So you go half angle.
Yeah, so I can, let's rewrite x. This would be, what would that be? We still coming up. How could I rewrite this better in terms of 2t as my angle? What's 2 sine t cosine t would be what?
Sine 4.
You're overthinking it?
4t sine. No.
So we write this like this. Twice 2 sine t cosine t is what's really going on there. And here we got plus 3y over 5, right?
You have a 2t in common.
How'd you get
Yeah, well, make it ahead. So what's 2 sine t cosine t?
Oh.
Sine
Plus.
Sine 2t is sweet, all right? It's just the sine 2t identity, all right? So you have to know those identities. The ones you have to memorize, you have to know them backwards and forwards. So this will be 2. This is sine 2t. If I know cosine of 2t is y over 5, what's sine of 2t? Don't overthink it.
X over
The
5.
opposite.
I like
The
that.
inverse.
Could it just be x over 5?
Well, no, you got to be careful because y is defined only in terms of t. X is its own variable. So if cosine of 2t is y over 5, where would y go?
How'd you get?
In the x place.
Sorry, yeah, Chris.
How'd you get the 3y over 5?
Yeah.
Oh, cosine of 2t is this, right? So replace cosine of 2t with this, and there you are. There's a cosine 2t,
Oh.
right? And what is cosine of 2t?
Wow.
Y over 5. Just plug and shove. Just replacing. So I don't solve this one all the way down to t. I solve it down to its trig functions because then I have identities take over. So dear God, I don't want to solve it down to inverse cosine of crap. I'd actually end up doing the same work, but it would just look so much worse. Because here I'm going to draw a triangle. Cosine of 2t is y over 5. So I have to figure out this side here, right?
Yeah.
Wouldn't y be the other thing?
So if cosine of 2t is y over 5, and you just gotta let go of the fact that this is like the y side. Cosine of 2t would be y over 5, right? Cosine is this side
Oh, yeah.
over that hypotenuse.
Mm-hmm.
Coolness. So I want to figure out what sine of 2t is. I gotta figure out that side.
5 squared minus 5.
Yeah, the square root of
5 squared.
25 minus y squared. Yeah, so this will be x equals twice rad 25 minus y squared over 5 plus 3y over 5. Yummy, yummy, yummy. Just to show you one other way you can eliminate the parameter. If you have trig functions in there, you can use identities, you can use triangles, you can use whatever the hell you need to eliminate the t. So if you have your calculators out, go ahead and put them in the parametric mode.
Oh.
Where'd you?
Thank you.
What's up? Oh, let's find out. There we go. We're going to do it together right now. Go sit down, dude. You're bothering me. Let's see. It's such a nice thing. Well, we'll do this all together. Because you just got to be careful about the way they define t. Here's a neat one. How do you do that one? Yeah. Alright, so let me clear this stuff out. If we put in here, let's do the first one first. So t cubed minus 3t squared. And then y was 2t minus 3. Now if I graph it, who knows what I'm going to get?
An S.
You gotta change
That's not right.
Beautiful. Exactly.
change your window.
So you got to change your window. So go to window, t is allowed to be from 0. I don't want that shit. I want it from -1 to 3. And the t step doesn't really matter. It's still stuck on for angles. So if I graph that bad boy, I'll change my window a little bit more. 0 to 6, yeah. I can't remember what it does to t though. Yeah, it takes it back to 0 to 2 pi, because it always assumes parametric is defined off of trig functions very often. So then it gets -1 to 3. It should give me back my Superman. Yes.
You could just go 0, 0.
All right. So the first thing is, are you in parametric mode? PAR. So when you hit y equals, does it show x1t, y1t? You there? And then you just got to plug in what x is, what y is. Cool.
For your window, you could make x -5 and 5 to look more like the graph on the paper.
There you go. Yeah, sure. Because our scale is -5, 5. Okay. Now let's try the second one. Let's take this out of here. We saw in rectangular coordinates that thing is not very pretty. So this graph should look kind of funky. So let's see, if we do 4 sine t cosine t plus 3 cosine 2t. Now let's go back to our window. How do you think I want my t? What do you think I want it to do?
You can leave it the same.
You could.
It shows up if you leave it the same.
But in general, if you're doing angles, how do you think you want it defined?
0 to 0.
Yeah, 0 to 2 pi.
You'll mention.
Sorry. So let's see, I'm in radians. Cool. If we go to a table.
You'll
Oh, okay, thank you. Y is 5 cosine 2t. I like that. So obviously, the way to completely define a point is x and y. I left my poor little y dude out, so the calculator was like,
No.
there you go, man. There's everything that's defined for you, buddy. So now let's see if I graph that bad boy. Sweet.
But you can circle.
It's not a circle.
Could be a frisbee
Could
going
always
towards your
be.
face.
Yeah, circles look really freaky on that, but it's definitely not a circle. It's an ellipse. But the really cool thing about this is it's been tilted, which is really difficult to do in rectangular coordinates, as you saw the result. But in polar, rotating these conic sections, rotating hyperbolas, ellipses, is relatively easy, right? Funky. So if you're not careful with your step, get a window. If I made my T step, if I made it 0.6, let's see what that looks like. Right? That's like me trying to draw an ellipse. So if you don't want to, if you want it out of Jeff drawing mode, put it down to 0.1 roughly for the step, because otherwise it's taking too large of a step in between.
Got it.
Is that cool?
Yeah.
And of course, depending on your calculator, if you have an old TI 83, maybe it's having some trouble. So you can try to figure out. Don't make the T step. It's going. Okay, go back to T step. Make sure it's not 0.05 or something crazy, right? Because that means it's putting a lot more points in to see what it's doing. Okay, maybe. So this is related to what I was saying earlier. If my function I put in is relatively moving fast, and I'm taking too big of a step, like we did -1, 0, 1, 2, 3 for the first equation on the handout, that might have looked like that if the thing was moving around too quickly. So I have to fill in some more points in between to see what it was really doing. Same thing will happen, of course, on the graphing calculator.
Could you explain this bottom one?
So again, going back here, let's take a look at what that looked like. So hopefully you understand, if I just change X and Y, I could actually put this into the graphing calculator. It would just be flipped, right? The screen would just be flipped. Is that cool? How did I get here? Is everybody cool with the 3y/5 piece? Okay. And then here we just replace that with something in terms of 2t, because I had information about angle 2t. Drew that from the information I have. Right? Cosine 2t tells me how to draw a triangle. Cosine 2t is y/5, so the x piece is y, the hypotenuse is 5. Why do I need to do all that? Because I want to know what sine 2t is. So then I can figure out what the y piece is, or let's say this piece. And then once I know what it is, I just throw it in. Not a big deal. So if you put y equals twice blah with x's in place of y, you get the same image on your screen in Cartesian. Okay, cool. And real quick, I just want to point out, let me boil this down a little bit better. This is x equals twice sine 2t plus 3 cosine 2t. So right there, what's the giveaway that this might be an ellipse?
2,
And
2t,
no? 3, 2 and 3. They have different coefficients. If I made it 3 and 3, this would be a circle. That's been rotated, so it's still a circle. Alright, is that cool? You guys with me there? A little bit? A little tiny bit?
Oh, that makes sense.
It's crazy how much sense it makes.
2, 3.
Okay. So,
Where'd that piece fit?
might be on the bottom. Let's try a couple more from the homework. Could you turn the lights back on, Mohammed? Thanks, man.
That's weird.
What's up?
I plugged that just with the y equals, it doesn't give me the whole thing.
Oh, yeah. Because I think when we took a square root, that's the piece. That's the piece I need to be careful with. When you do the triangle and you get the other side, I have to take a square root to get it. So you have to do the plus or minus. You actually have to put y1 and y2.
Oh, okay.
So when you do 1, you get the top part of the ellipse. Yeah. When you do the negative of it, you get the bottom part. Just for the part you had to do the plus or minus, the square root of 25 minus y squared. That piece?
Yeah.
Yeah. Cool. So let's see what kind of stuff. In the homework, starting at number 3, that section, it just says sketch the curve. So you do just like we did there. You make a little TXY table. And you go to town?
And you can plug in a calculator, right? And do the.
Certainly. And then it says find a rectangular coordinate equation. So you just, normally you solve for t if it's just polynomials in t. If it's trig functions in t, so for example, if I had this, let's try two of these out. Well, it's not too bad. Let's get something freakier. So when you're doing the homework, they tell you that pi, t is from 0 to pi. That's what it is we're trying to say. And of course, at 0 and pi, that's where cotangent and cosecant are. At 0 and pi, that's where they are undefined. I love it. That's why they don't allow it to be there. Cool. I like it. So it'd be easy enough to make a little TXY table to plug stuff in, right? So forth. You can use angles that you know or not. Just get decimals and go for it. How do I get t? How do I get rid of t? How do I get y as a function of x, or at least the relationship between x and y? How do I do that?
Substitution.
Okay, sure.
The inverse? Yeah,
Okay, sure. That'll actually work. It's not too horrible here. There's not a lot going on here. But from this point, even, cotangent of t is x.
X over.
Yeah, cotangent of t is x. But then cosecant of t's got to be y. So I guess it's not too bad, right?
X over y and no.
X minus.
Or let's try this. Is there an identity that relates cotangent and cosecant somehow?
Yeah, the cotangent squared
Yeah, there's the cotangent squared.
plus 1 equals cosecant squared.
So if I took both of these and
Squared them.
squared them, then I could just plug into this equation, right? Instead of taking it, I got t. Put in place of this, put x squared.
Plus 1 equals y. Yeah.
Kick ass. Of course, if I kept going with this, if cosecant of t has to be y, where would y have to go? Be careful. So let's see, did I put x in the right place and stuff here? No, I didn't. What's cotangent of t is x, so where should x go?
On the bottom.
Yeah, there we go. That's better. Now, y is supposed to be cosecant of t.
That's sine.
And actually, let me just do this. Let me finish this out. Because to get cosecant, what do I need?
1 minus x. No, 1 plus x squared.
I need this side over that side. Yeah, so this would be 1 plus x squared. So what's y equal to? Cosecant of t. So what's the cosecant of t? What's the cosecant?
Square root.
Square root of 1 plus x squared over 1. Because cosecant is like sine, right? Over 1. Ooh, I did it.
Yeah.
Square both sides, you get there.
Ooh.
I mean, so there's two main ways to do the trig stuff, either directly through identities or using triangles. If you did solve for t, you would eventually have to use a triangle because you get the inverse cotangent, and that sets up a triangle, right? So that wouldn't even kill you. But it gets really ugly. There's a lot going on up here if you try to do inverse stuff.
I got confused right after you wrote equals that one.
Right after that?
Yes.
Or right
So
as I
I
did.
draw after that.
So you're cool with it up to here?
I'm cool. But
Oh, then you're good.
I just plug in cosecant.
No, yeah, because y is the cosecant of t, and the cosecant of t is this. So is this the relationship between y and x?
Yes.
Okay.
You're done. You're done. So you use that information to kill this thing. You didn't want this thing. So this is a very, very subversive substitution. Right? It's not even
So
as...
it's the same thing, or it's substituted, but
So
at
it's
the
the
same
same
time
triangle.
This sets up a triangle, and this says y is this piece of the triangle.
you convert it.
So you just write the things in terms of x, and then you got y in terms of x. Yeah.
So basically, for this whole thing, you're just trying to get rid of the t.
Yes.
So I mean, they tell you directly. They say eliminate the parameter. They want to get just the normal x, y equation that we've seen a million times. Just get t out of the way. Sometimes it's easy. Sometimes it's remarkably difficult to do. Right? You won't get a lot of the remarkably difficult ones. Don't freak out.
Yeah.
Not in 176. Okay. Let's try one more of these. Maybe something without any trig stuff here. We'll have this one here. This one isn't too bad. I want to show you a little quicker way to do it.
So the x at the bottom.
Yeah.
Good. Alright, so you get t over x.
Oh,
That
but we need
sucks.
to eliminate the t. Right.
It's not bad. If
Well,
x is
but
t plus 1, what's
Minus
t?
1. T equals x minus 1.
There you go. So then y is
X minus 1.
x minus 1
Over x.
over x, yeah. Do you start to see, I mean, I'm going to show you a few of these so you start to see what to look for. I mean, some of these are going to be remarkably quick. Now, if you didn't see all that mess, that's okay. If you don't see anything to do other than solve for t, then you do it. So if you say t equals x minus 1, now just replace t with x minus 1. Replace t with x minus 1. And you still end up at x minus 1 over x. I don't care which way you do it. All right, maybe.
Mm-hmm.
So again, all I did was solve for t. So get t by itself in one of these equations, and I'd much rather get t by itself in this equation. Once you have what t is, you can plug that into the other equation. You could do that every time, but my God, sometimes it makes it the worst it could possibly be. Right? But you can still do that every single time if you really wanted to. Sometimes there are really, really quick little tricks, and if you don't see them, then you do it this way. It doesn't kill you. Not yet. I haven't had anybody heal over because of that. What's up?
You said down here find t, but what did you do up there? Found t.
Yeah, except we used the fact that I already knew that the bottom was x.
Oh.
I didn't have to put t in there. It's not a big deal, but it's a small example of the type of thing you can do to make these problems quicker and easier. You can look for these kind of relationships and get there quicker. Or you can just pure, by force, get t and plug it everywhere t is, and then try to simplify it. Right? That will also work.
Mm-hmm.
Okay? So let's see, that's number 3 through 24. Ask you to graph it and then to put it to eliminate t. Blah, 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 blah. Yeah, that's pretty much all they give you. Okay, cool. You can see some of the images you can come up with, like on page 570. This is where I hope at least some of you guys just play around with that calculator like I did when I was a little kid. I was playing around with the ones that weren't graphic calculators. They were just the old-timey red symbols on the screen, the first calculators that came out. I was in the corner going, oh, wow, I'm going to be weird when I grow up.
Like I made it say boobs. That's you.
Pretty much. That's well, yeah, that came out too.
Boobless.
All right.
Oh yeah.
Boobless, exactly. So any questions from section 8.4 before we get into chapter 10? I really want to focus on 10 for a while. Yes?
Can you do number 15?
This is a good example of one that looks. Now, how do you mean? You want to graph it, or do you want to solve to get fill the t?
Yeah.
All right. The very first thing you look for when they ask you to kill the t is there already a direct relationship between what I see? So let me write this in a different way. It might be because of this way this is written. What does sine squared t really mean? It means sine of t, whole thing, squared. And what does this mean? It means sine of t, whole thing, fourth power. So then I would say that, what would I do to this to make it this? Squared. So to get y, I would take what x is and square it. Dude! So that's a really good question, because it's the first thing you look for is there just a direct, is x t plus 3, and y is 4t plus 12. Well, then y is 4x. Bam, done. Dear God, don't solve for t even. Right? That's one of the first things you look for is there a direct relationship between these two things? And then if there isn't, you do everything else you were doing. Yeah. Cool. I like it. Right? So don't start getting really freaked out about, oh my God, these are disgusting. Power reducing formula. No, shit. Don't do that unless you really, if that was cubed and that was a fourth power. Even that would be horrible, to be honest. So let's see. 15 stop.
Can you? Yeah.
Yep, that's it. So again, I don't see a direct relationship. So what I do is maybe when I have trig, most of the time I at most want to solve down to just sine, cosecant, tangent, and then I can throw them into identities, right? So if x is sine cubed, sine is how related to x?
X to the
Cube root?
Yeah.
Or x to the 1/3, maybe even better. I like it. And then you can just plug it in. If x is sine cubed, sine is the cube root of x. And then what is y doing to sine? To the fourth power. And what is sine t?
X to the 1/3.
So y is x to the
4/3.
4/3. Get out of there. Come back. But again, it's sort of like, it's not as bad as trig identities themselves, but it just takes a couple of examples to show you what you're allowed to do, what you want to look for. And in general, I would highly recommend you almost never take trig functions all the way down to t. Just make it look worse than it needs to. Sometimes you might need to, but most of the time you don't. Okay, cool. All right, so some of you guys don't want me to get to 10 right now, but let me tell you this. Section 10.1 and 10.2, if you have any trouble with them, you did not belong here. 10.1 and 10.2 is completely review. 10.1 and 10.2 is addition, subtraction, the addition method of solving, substitution method of solving a linear system of equations. 10.2 is if I give you 3 letters. Ooh, that should have freaked you out when you were in Math 90, but now it should not freak you out. You should go, give me more of that. So let me just make sure that we all remember how to do this. Now obviously if you get through parametric, you should remember how to do substitution method, because that's what you pretty much always use. So let's see, if I give you this here. Oh, what you got, Jeff? I don't know, man.
So this is now chapter 10.
Yes, it is.
Hmm?
This is chapter 10. It's 10.1. Oh, what was I doing? Let's see. What method would you not want to use unless I told you you had to?
Subtract.
Substitute. Good Lord, man. You get all these fractions, which really shouldn't bother us, but then anytime you can eliminate, you can avoid dealing with fractions, you do, because they're an easy place to make mistakes. I don't care how good you are in that. So I'm not going to do substitution method, dear God. So of course, what method are you going to use? Elimination, cool. Addition, subtraction, elimination method. So what variable are you going to eliminate?
X. I don't know. Oh,
Why is y just a little bit better?
Oh, negative and
Because
positive.
they're already different signs, and negatives are another place I can make easy mistakes. So if I already have two that are opposite signs, I'm pretty much going to use them unless their coefficients are just really disgusting. So of course, the whole idea with elimination is if only that was a 4 and that was a 4, they would cancel, right? Since they're opposite signs. It's LCD kind of idea now, right, instead? So what's the LCD of 4 and 5?
4 and 5. Well, 20.
20. Cool. So you're going to multiply the first guy by
5.
5. And the second guy by
4.
4. And then we all get to see if Jeff thought of this correctly in his head.
I think you did.
Is X equal 1?
Yeah! See, Jeff is giving himself a break. So 49x equals 49 when you put those together. So x is 1, so therefore y is, I just got to plug it into one of these. If x is 1, subtract 6, you get 15. Divided by 5 is
3.
3. Kick ass. Alright, so that should be like, oh my god, dude. After all this trig, and polar, and parametric, you get a little, yeah, exactly. That's why I wanted to get here. So 10-1 and 10-2. 10-2, let me give you one of these, and then we'll talk about some new stuff. Because this is all review. 10-2 would give you this. I think to be safe, I don't want to rely on my brain to come up with something that actually works nice. Take one out of here. So of course you see a pattern in this. If I have 2 unknowns, I need 2 pieces of information to figure them out. If I have 3 unknowns, 3. If I had 18 unknowns, I would need 18 equations. Right? So we're going to come up with a method in section 10.3 that would make solving an 18 equation problem as easy as solving this problem.
Okay.
So by hand, I don't know if you guys remember, how do you do this problem?
Find 2 variables and then substitute. And that's how
You could, but sometimes that will introduce very disgusting fractions, which, again, that's a very direct way to do it as long as you just deal with the fractions. It's cool. We're not there yet. Right. So some of you guys, how many of you guys learned about matrices in Math 110? Kick in. So that's where we're headed. Some of you guys didn't, so it totally depends on your teacher, if they did it or not. I'm going to assume that, since some of us didn't, I'm just going to assume nobody has. Right? So, in fact, section 10.1 and 10.2 assumes you have it, so you're not allowed to use matrices in 10.1 or 10.2.
No. But we learned that before.
So in section 10.3 is when you officially know in Math 176 matrices. So 10.1 and 10.2, if you try to use them, I'm going to make you redo it. I mean, come on. Why would you expect anything else? So, how do I do this by hand?
Can you multiply the top one by 2?
You totally could. This one happens to have a really beautiful multiplying
by a negative.
Your 2 y's is easy.
First and second.
You add those
Which letter is easiest to kill?
y.
The y's. And I can do it. How many times must you do it?
Twice.
So if I kill the same letter twice between 2 different sets of equations, I get 2 equations with 2 unknowns that we know how to do.
Yeah.
Right? So if I take 1 plus 2, because they're already different sides, what do you get?
X, 2x
2x
minus 2z or
plus 2z
equals 14.
14, so I get x plus z equals 7. Is that cool?
Yeah.
So that's equation number
1.
4.
Oh.
I like that. So we call that?
Yeah.
Right? So, and this one happens to be, if I take 1 and I can't combine it with 2 again, so instead I combine it with
3.
3 because they already are opposite signs in the same coefficient. That's really nice of them. If they weren't, we would just do what we did over here. So if I take 1 plus 3, what do I end up with?
4x.
4x
Plus.
minus 2z equals 4. So I get 2x minus z equals 2. That's equation number 5. It should be very familiar. And then, of course, between these two, what can I do? Kill the z's. Exactly. This is a very simple example because they already are exact opposites of each other. If they weren't, I would just multiply one or both of them. So if I take 4 plus 5, I'll get
3x
3x.
equals 9, so x equals 3.
equals 9. I like it. So x is 3.
And then plug it in.
And the minute I know 1, when I teach this, I normally call it dominoes. Now you set your dominoes up, you let them fall back. If x is 3, you go back.
Z is 4.
Z must be 4. And if z is 4, you go back into any of these. Is everybody with me? So now that I know 2 of these things, go back to the one that has 3. And I'll get, for example, 3 minus 2y plus 12 equals 1. So I get 2y equals 14. Is that true? Yeah. Y is 7.
No.
No, because I added 2y and subtracted 1. I made the y piece positive. Is that cool?
Yeah.
Yeah. So y is 7. So actually, how should I really write that answer?
X, Y, Z.
X, Y, Z. I love 3, 7, 4. Because in reality, each one of these defines what geometrically? Each one of these defined a line.
Okay.
And this was the point where they
Intersected?
met. Exactly. Because it has to be true for both lines. So a line is just a visual representation of all the answers to that equation. So what answer works in both? Where those two things meet. That's the one point that works in both. So this is a little bit more interesting. Now I'm in 3 dimensions. So each one of these defines a plane, like this wall. So that could be this wall, that could be that wall, and that could be the ceiling.
And the point is that.
So if that's true, what's the solution visually? That corner. That point there, right? Now obviously, planes don't have to be, they could all 3 be parallel to each other. Or 2 of them could be parallel and the third one's coming in. So just the same way that 2 lines could be parallel and have no solution, there's actually a lot more orientations for 3 things, 3 planes to not have a solution. They just don't have to agree on a single point. They could do, if you look from above, they could do this kind of thing. Us, when I look from above, they did this kind of thing.
Mm-hmm.
Because with me, if I was looking from above, so this is an entire plane, so somehow we are away at infinity looking down, and we can see that they met at one point. But it's really easy for them not to. So it would be really easy for this to not have any solution. And of course, what would come out if this did not have a solution?
0?
What kind of thing would you see? 0 is okay.
No number that really.
Oh, like 3 was 4.
You get somewhere in there, you get 3 equals 4. Something telling you, dude, this ain't going to work.
What do you say? Right? Do you
You
just
write no solution.
Okay.
Yeah. And just as easily, it could have an infinite number of solutions. So real quick, if my planes were this wall, the ceiling, and some third plane coming in like this, I didn't bring. Say again?
Would you say that wall, and the ceiling?
No, because then there'd be no solution.
Oh.
So this wall, the ceiling, and another wall coming in right there, the answer would be this line of points. It'd be an infinite number of things on that line. Okay, so you can have all the same weirdness as before.
Can't they be on like the same plane as well? Can't you have that?
Oh yeah. Yeah, I mean the planes could overlap, so they could be dependent on each other. Oh yeah, it's a little early.
Are we going to get that?
Maybe. It's a little much.
Next time.
So you guys, real quick, let me say this at least. You got tomorrow off, so just I don't want to hear any groaning. Keep it to yourself. Internal groans. You should know how to do that by now.
No.
Real quick. What was the big thing with synthetic division?
I don't remember.
Oh,
What was beautiful about that? Instead of having to do this kind of weird shit like this,
No, yeah.
You just
Numbers change.
you just dealt with the coefficient.
all that really, the most important parts, I was carrying around all this extra bullshit that I didn't care about, right?
Just the coefficient.
So we just said, let's look at the numbers. So a lot of you raise your hand, you've done matrices before, but if you haven't, the main idea with the matrix is, the matrix that goes with this equation, these equations would be just looking at their coefficients. So it'd be
1,
one,
-2, 3, 1.
yeah.
1, 2, -1, 13, 3, 2, -5, 3.
So I always draw that line there. It's kind of like my equal sign line. So this is the real matrix of variables, and this is the solution part. So this is what's called an augmented matrix, sort of like augmented reality. So augmented matrix, it just has something added to it. And we're going to learn, and of course a lot of you already know, how to row reduce this bad boy and have the answer just kind of show up. And once you learn that process, I don't care how many rows and columns I add, the same process just attacks it. It's wonderful for programming computers to do it. Computer would just eat it up, make our one kill, right? You sound really close to it, they can hear, make our one kill humans, what? No. All right. Oh shit! You're supposed to remind me about that. You're supposed to talk about that.
Yeah, should I email you or should I just?
No, not that many people doing it. It's I've already heard it.
Do on Thursday.
Yeah, on tomorrow.
I haven't started.
From my discussions with him, and I've seen him teach them. It's great.
Well, I
I personally think
it's my bullshit
too many
class.
little
not
minor
mine.
devices and tricks that get students through, but then maybe later
So I got to an 88.
minute. But he doesn't use a ton of it. Just and he specs a lot on his students, so I'm still cool with that. Yeah. So he's really good. The students all love him. Constantly doing that.
For who?
Just remind me, Court.
Oh yeah, Corey's good.
Remind me of when they get more general.
They said
not
Milan too.
Wednesday.
Milan is another good one.
Yeah.
Oh, Arturo, yeah, I wrote down 3. Someone did great phone, got like question marks. Yeah,
I heard phone
Wow.
yeah.
is hard.
We're ranked third,
No, I'll try to get one of
so
the
they
Arturo.
so we win all of our games for
Are you priority registration?
What?
Do you have priority registration?
Yes.
So you're probably crashing. Well, Manchester shouldn't be too bad because it's going to be on Friday.
Okay.
So
I haven't even looked
I
at
just wanted to give you a heads up, because I told you that
Yeah.
no, like Manchester's
I haven't picked up at all.
because he's teaching a class on Friday.
So I don't even
there's
know
gonna
where
be
you guys are. Now I do. All right, good. Good.
We'll see.
Yeah.
I don't know.
Slaughter.
You're taking it next semester, right?
What?
Alright.
But I have priority registration, so
Good.
I'll
Good.
get
You
Manchester.
should. I like that. Good. Keep it going.
Do you know
I'm not
where
last
the
semester,
leaking is
because I
happening
didn't-
now? Like, where exactly it is?
Oh.
Did you call?
Yeah, I called them, but they didn't tell me like where it was.
Oh, so yeah, it's over here where financial aid and all that is. So if you walk into that building, they're the first little area to the left once you get past
Is it like
it.
the one building, like, where you, like, when you first come, like...
The cashier's outside,
Is it like-
financial aid, and
You know when you take the...
admissions is in there.
The,
oh yeah, the assessment office.
Yeah.
Yeah, exactly.
Okay.
So if you took it over there,
Yeah.
that's where it is.
Okay.
Cool.
Thank you.